Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from Allen Institute for AI Olmo 3, fully open long context reasoning models and their full model flow. Olmo 3 is a new family of open language and reasoning models at 7 billion and 32 billion parameters. They're built not just for generic chat, but for hard tasks like math, coding, long context reasoning, function calling, and knowledge-heavy question answering. What makes Olmo 3 stand out is that it's fully open. The team releases not only the final weights, but also the data recipes, intermediate checkpoints, and training code. Their flagship model, Olmo 3.1 Think 32B, is currently one of the strongest fully open reasoning models available. Most open weight models give you a single endpoint, the final checkpoint. Olmo 3 takes a different stance. The authors argue that to really advance OpenAI research, we need transparency over the entire model flow. The full lifecycle from raw data to pre-training, mid-training, long context extension, and post-training. By releasing data mixes, code, and intermediate checkpoints, Olmo 3 lets you reproduce the models, audit them, and study how capabilities emerge. It also lets you intervene at any stage, not just slap a fine-tune on top. The Olmo 3 release is actually a family of models. Olmo 3 base at 7B and 32B is the foundation, trained to be broadly capable across language, knowledge, math, and code. On top of that, Olmo 3 Think adds explicit chain of thought style reasoning, where the model writes out its thinking before answering. Olmo 3 Instruct is tuned for everyday use, short, direct answers, and strong function calling behavior. Finally, Olmo 3 RL0 is a set of models trained with reinforcement learning directly from the base, designed to help researchers study how RL interacts with pre-training data. Olmo 3's training pipeline has three main base model stages, followed by post-training. First, pre-training. The models see about 5.9 trillion tokens from a curated mix called Dolma 3 Mix. Second, mid-training. An extra 100 billion high-quality task-heavy tokens sharpen math, code, QA, and early instruction and reasoning skills. Third, long context extension. Another 50 to 100 billion tokens extend the context window up to 65,000 tokens. On top of these base models, the team runs a three-stage post-training recipe: supervised fine-tuning, preference tuning with DPO, and reinforcement learning with verifiable rewards to produce the Think and Instruct variants. Training the 32B Olmo 3 models is a substantial but clearly quantified effort. From the start of pre-training to the first Olmo 3 Think 32B checkpoint, about 56 days pass on a cluster of 1024 H100 GPUs. Roughly 47 of those days go into pre-training, mid-training, and long context extension. Another 9 days are spent on post-training, running multiple SFT, DPO, and RL sweeps and evaluating many checkpoints. At a notional rate of $2 per H100 hour, the total cost comes out to around $2.75 million. The authors emphasize that a non-trivial fraction of compute goes into evaluation and post-training. Olmo 3 Base is designed to be a strong general-purpose foundation. Architecturally, it's a dense decoder-only transformer, closely following Olmo 2, but scaled to 7B and 32B parameters and upgraded for longer context. Pre-training and mid-training use an 8,192 token window, with sliding window attention in most layers to keep compute and inference costs manageable. Training runs on the Olmo core codebase, which uses PyTorch compile, custom attention, and LM head kernels, and asynchronous logging and checkpointing to reach respectable hardware utilization on H100s. The team spends a lot of effort on evaluation design. They point out that many benchmarks are noisy and that small models often sit at chance on hard tasks, making them poor guides for data decisions. To address this, they build Olmo Base Eval, a 43-task suite tailored to base model development. Tasks are clustered into capability groups like math, code, multiple choice STEM, non-STEM, and generative QA. There's a base easy suite that uses bits per byte metrics for small models, a base main suite for larger runs, and a small held out set, MMLU Pro, DeepMind Math, LBPP, and BBH. On the Olmo Base Eval main suite, Olmo 3 Base performs very strongly. At 32B, it's the best fully open base model, clearly beating Stanford Marin 32B and Apertus 70B on math and code composites, and coming within a few points of strong open weight baselines like Qwen 2.5 and Gemma 3. On multiple choice QA, it tracks Marin and Olmo 2 closely, and sits just behind the very largest open weight models. At 7B, Olmo 3 base is the strongest fully open model on math and code, with sizable margins over Marin 8B, Apertus 8B, and Olmo 2 7B, and it's competitive with Quen and Nematron Nano on these skills. The pre-training data for Olmo 3 comes from Dolma 3 Mix, a carefully curated 9.3 trillion token pool from which a 5.93 trillion token training mix is drawn. The main sources are Common Crawl web pages, a new large-scale collection of academic PDFs processed with Olmo CR, GitHub code via StackEdu, math-heavy web pages from FineMath, and Wikipedia and Wikibooks. The authors follow two principles: only include sources that are large enough to matter at trillions of tokens, and keep structured task-style data mostly out of pre-training, reserving it for mid-training and long context stages where its impact can be better controlled. The Common Crawl portion of Dolma 3 goes through an aggressive cleaning pipeline. HTML is stripped with Razilla parse, then documents are filtered by URL, length, character composition, and internal repetition, and non-English or spammy content is removed. After that, the team runs 3 levels of deduplication: exact hash-based dedupe, min-hash-based near-duplicate removal with Jacquard verification, and a suffix array-based pass that strips repeated boilerplate substrings. To make this scale to tens of billions of documents, they built Duplodocus, a Rust-based tool for large-scale exact and fuzzy deduplication. Once the web data is cleaned and deduplicated, it's annotated by topic and quality. A distilled web organizer classifier assigns each document to one of 24 topics, and a fast text-based model scores quality. Within each topic, documents are bucketed into 5 percentile quality tiers. To decide how much of each topic to use, the team trains a swarm of small 30M parameter proxy models, each on a different mixture sampled from a Dirichlet distribution. They then fit regression models from mix weights to performance, and solve a constrained optimization problem to pick topic ratios. Within each topic, they apply quality-aware upsampling curves that discard the lowest quality data and repeat the best material a few times, rather than just hard filtering. After pre-training, Olmo 3 base gets an extra 100 billion tokens of mid-training on Dolma 3 Dolmino mix. This mix is heavily targeted. It includes new synthetic math datasets like TinyMath and CraneMath, synthetic code like Crane Code, QA datasets such as Reddit to flashcards and Wiki to RCQA, and a variety of thinking trace datasets spanning math, code, and general reasoning. At the same time, the mix retains some high-quality web and PDF data to keep the distribution from drifting too far from pre-training. The goal is to boost core capabilities, especially math, code, QA, and early instruction following, without overfitting to any single benchmark. To build the mid-training mix, the team uses a 2-level methodology. First, microanneals. They take a pre-trained checkpoint, train it for 5 to 10 billion tokens on a candidate dataset plus web baseline, and compare performance to a web-only anneal. This gives a cheap signal about whether a dataset is helpful. Second, integration tests. They assemble full 100 billion token candidate mixes, run mid-training, and then quickly SFT tune and evaluate to see how gains carry through post-training. They also introduce a new decontamination tool, Decon, to scrub mid-training and long context data of benchmark leakage. Interestingly, they find that contamination sometimes inflates scores, but in other cases, decontaminated data actually performs better, especially when contaminated formats don't match eval formats. One of the key findings from mid-training is that there are real trade-offs between domains. If you heavily skew the mix toward math and code, you can get excellent gains on those tasks, but you lose performance on multiple choice and generative QA. If you skew toward QA and instruction data, you don't gain much on QA, and you hurt math and code. The final Domino mix is a compromise that balances these domains. Another interesting result is that including instruction data and thinking traces in mid-training improves base model metrics across the board, even before any post-training. That suggests that some post-training style data is beneficial earlier in the pipeline. To extend context length, Olmo 3 uses long academic PDFs from the Olmo OCR pool, many of which are tens of thousands of tokens long. They augment some of these with synthetic aggregation tasks, like counting occurrences of key terms or rewriting content in different formats, to teach the model to use long context meaningfully. The long context mix is about 1/3 long documents and 2/3 high-quality short context data from mid-training, which helps preserve short context performance. They apply yarn positional scaling on full attention layers, use best-fit document packing with intra-document masking, and train with context parallelism so each device handles a slice of the 65,000 sequence. The extended Olmo 3 models are evaluated on two major long context benchmarks. Ruler, which focuses on synthetic long context tasks like needle in a haystack and aggregation, is used during development. Helmet, a more diverse suite of long context tasks, is held out for final evaluation. At 7B, Olmo 3's long context performance is competitive with Llama 3.18b, Qwen 2.57b, and Nematron Nano 9b. At 32B, it's in the same ballpark as Qwen 2.532b, Mistral Small 3.124b, and Gemma 327b. Notably, these results are achieved with relatively short extension stages, 50B tokens for 7B and 100B for 32B. Olmo 3 Think is built with a carefully layered post-training recipe. First, Dulce Think SFT provides supervised data, high-quality reasoning traces and answers across math, coding, precise instruction following, science, and general chat. Second, Dulce Think DPO adds preference data, pairs of better and worse completions constructed using the delta learning idea, where the key signal is the quality gap between them. Third, Dulce Think RL uses about 100,000 props across math, code, instruction following, and chat, each with either a verifiable reward or an LM judge score. These three stages, SFT, DPO, and RL with the Olmo RL algorithm, stack to produce strong reasoning models. Olmo RL is the reinforcement learning framework used for Olmo 3 Think and RL 0. It's based on group relative policy optimization but with several important tweaks. The loss is normalized at the token level to avoid length bias, and they use truncated importance sampling to correct for differences between inference and training engines. The clipping range is asymmetric, allowing slightly larger positive updates than negative ones. They drop the explicit KL penalty, relying instead on the structure of the objective, and they compute advantages without dividing by standard deviation, which avoids over-amplifying very easy or very hard questions. On top of that, they plug in domain-specific verifiers, symbolic equivalents for math, unit tests for code, constraint checkers for instruction following. On the post-training evaluation suite, Olmo 3.1 Think 32B stands out. It's the strongest fully open thinking model at its scale, outperforming Qwen 2.5 32B Instruct, Gemma 2 and 3 at 27B, DeepSeek R1 32B, and various distilled Qwen models on math, reasoning, coding, and instruction following benchmarks. It also comes close to Qwen 3 and Qwen 3 VL32B, despite being trained on roughly 6 times fewer tokens. At 7B, Olmo 3 Think is competitive with leading open reasoning models like OpenThinker and Nematron Nano 9B, and substantially ahead of many earlier 7B scale thinking models. The authors carefully analyze what each post-training stage contributes. Supervised fine-tuning on reasoning traces gives a big initial jump, but quickly saturates. Continuing to imitate more traces can even hurt. Preference tuning with DPO using delta learning style pairs where the chosen answer is only relatively better than a weaker one pushes performance beyond what SFT alone can reach. Reinforcement learning with verifiable rewards then adds another layer of gains, especially on math, code, and precise instruction following. They find that RL works best when initialized from the DPO-tuned model rather than directly from SFT, and that mixing RL data across domains helps avoid over-optimization on any single metric. Olmo 3 Instruct is tuned for everyday use. You want a helpful answer quickly, not a long chain of thought. The SFT stage, Dulce Instruct SFT, includes general chat from WildChat and Open Assistant, safety data like Coconut and WildGuard Mix, science QA, logic puzzles, and multilingual chat from Aya. It also adds new function calling datasets, including real interactions with MCP tools for web search and scientific literature. The DPO stage, Dulce Instruct DPO, adds preference pairs that emphasize multi-turn quality and explicitly control for length, so the model doesn't become overly verbose. Finally, Dulce Instruct RL uses a mix of math, code, instruction following, and chat prompts to refine capabilities while preserving usability. For function calling, Olmo 3 Instruct uses a consistent format. Tools are described in OpenAPI style, and calls are represented as Python-like code blocks wrapped in special tags. The models are evaluated both intrinsically, using the Berkeley function calling leaderboard, and extrinsically, as agents using MCP servers for scientific literature and web search. On tasks like Lit QA2 and Simple QA, having tools available significantly improves accuracy compared to relying on parametric knowledge alone. Overall, Olmo 3 Instruct 7B and 32B outperform many comparable OpenInstruct models, including QN 2.57b, Olmo 2 Instruct, Apprentice 8b, and several others, while remaining concise and tool-aware. Olmo 3 RL0 is a separate line of experiments, where reinforcement learning is applied directly to the base model, without prior SFT or DPO. The team trains RL0 variants on math, code, precise instruction following, general chat, and a mixed domain. For each, they build Dolce RL0 datasets that are carefully decontaminated against pre-training and mid-training data, so improvements can't be explained by memorized evals. RL0 is meant as a clean benchmark for the RL community. It exposes the full data pipeline and lets researchers test RL algorithms and reward designs without hidden contamination confounds. The RL0 experiments show that reinforcement learning from the base model can substantially improve math and other capabilities. The domain trade-offs appear when training on mixed data. Single domain runs can push train rewards very high, but risk over-optimization. Mixed runs achieve more balanced improvements. The team also ablates algorithmic choices, active sampling, which keeps batches full of non-zero advantage samples, stabilizes training, and infrastructure optimizations like continuous batching and in-flight weight updates dramatically speed up RL. Finally, they run a negative control where rewards are random. In that setting, evaluation scores do not improve, which is strong evidence that their decontamination pipeline has removed eval leakage from the training data. Despite its strengths, Olmo 3 has clear limitations. Training still requires millions of GPU hours and trillions of tokens, which is out of reach for many groups. The team documents real trade-offs between domains. Pushing math and code too hard can hurt QA, and vice versa. The post-training recipes for DPO and RL are still somewhat empirical and sensitive to hyperparameters, data mixes, and reward definitions. Long context extension, while relatively efficient here, is still expensive and heavily dependent on architectural and positional encoding choices. These are all open areas for further research. Stepping back, Olmo 3 is as much about process as it is about raw performance. By releasing the full model flow, data recipes, code, and checkpoints, the authors create a platform for serious scientific work on how large language models learn. Olmo 3 base at 7B and 32B is a new high watermark among fully open models, especially on math and code. The think and instruct variants demonstrate that carefully layered SFT, DPO, and RL can yield strong reasoning and practical chat behavior. And the RL0 line, together with the Dolce datasets, offers a clean, transparent benchmark for the RL community to explore algorithms, rewards, and data effects. For anyone interested in open, reproducible LLM research, Olmo 3 is a major step forward.